Good morning. So the camera is working today, so I hope to be recording these lectures starting today and continue to post them. One question I have for all of you is, do you all have a copy of the textbook, either 9th edition or 8th edition? Now, do you have it with you now? If you have it, please get it out and have it on the table. As we discuss each topic, I'll be just doing examples from the book, especially end of chapter problems. So thank you. Happy somebody's doing this. Thank you. So I really suggest that you bring textbook to the class and keep it with you open so that we can save some time reading out and doing problems. How many of you have the textbook today? That you have, right? Okay. Anyone else? Did you purchase the textbook? Just didn't bring it today? You didn't purchase yet? You should. Or at least you should have access. You can borrow, do whatever, but have the textbook. We need to do problems. Okay. So let's get started with that. Any questions from last lecture? No? Okay. So towards the end of last lecture, we wanted to make the point that molecules or atoms have a weak attraction when they are far apart, and a strong repulsion when they are squeezed too close to another atom or molecule. I'll just say atom. So if you have, we'll just simplistically represent this as two spheres. It can be something like a helium atom and a helium atom. The force between them looks something like this. It's repulsive when they are very close, and it's attractive when they are a little bit far away. So this is repulsion. So I'm talking about force here and separation. Repulsion when they are close and attraction when they are far. And this nature of the force between atoms and molecules is the reason why we have them to cohere and form structures, or in other words, if you have atoms, or sorry, come back to a material, I told you that depending on external factors or external variables, and those variables are pressure or normal stress, shear or tangential stress, and temperature, which is a measure of, what is temperature a measure of? Total kinetic energy of the molecular or atomic motion. Thank you. So a material, depending on external variables that are pressure, shear, and temperature, can exist as a fluid or solid or combinations thereof. I'll let you write this and then I'll ask you for example. We want to get examples for materials that have distinct fluid behavior and materials that have distinct solid behavior and materials that are sort of in between. I'll get it started. So when I say fluid, talking about water, talking about air, talking about mercury. And when I say solid, talking about material like steel, titanium, so on, and rocks. What did I say last lecture about the subjective, the conditions on which this is a solid or this is a fluid? Circumstances. Suppose if you are in the middle of a volcano, the rock will flow. We call it magma. So in that context, it is a fluid. But under regular conditions, a rock is a solid, rock solid. That's the phrase, right? And water, well, you have to ask me the question. When you say water, what pressure and temperature are you talking about? Are you talking about regular, like room temperature, or am I talking about temperature that is in the North Pole, or am I talking about what the conditions inside a pressure cooker where, do you know what's the boiling point of water inside a pressure cooker? Anybody? Is it 100 degrees Celsius or more than 100 degrees Celsius? It's more than. When pressure increases, the boiling point goes up. When pressure decreases, boiling point comes down. That's why if an astronaut is in outer space and their spacesuit has a leak, the biggest risk is their blood will boil away, because at that low pressure, the boiling point of water also comes down, that it can spontaneously boil off at room temperature. Anyway, that's a fun fact. So there are fluids which have fluid behavior, which is that what is fluid behavior? They deform continuously. They deform continuously when subject to shear deformation. I'm sorry, shear force. Solids, on the other hand, what punctuates a solid? They have
Rigid.
they are rigid because they are rigid. That's an outcome. Why? Because they have restoring forces at the molecular level that bring the atoms back to position and give them the shape back. In a fluid, those forces are much weaker. So once you shear a puddle of water, it just deforms continuously because the forces are so much weaker there, or almost they are non-existent. At the molecular level, to bring them back to original positions after the force is removed. This is classic, right? Hooke's law. What do you do in your Hooke's law experiment? Anybody? You hang a big weight on a steel bar, you watch it deform, you note the force, you note the deflection, and then you try to calculate spring constant. What happens when you remove the load? The object regains its original dimension. Is this making sense or totally new? Okay, that is what a solid is. It has that restoring force at a molecular level, which brings it back to its original shape. That's the most ideal form of solid. The ideal form of fluid is one that deforms continuously when subject to a shear force, and corollary, it cannot be restored to its original shape. So there are fluids, there are solids, and any examples for things in between? Something that's almost fluid but has some solid-like properties, something that is almost solid but has some fluid-like properties. Louder please.
Toothpaste.
Toothpaste. Toothpaste goes back and forth. I'll write it here, but toothpaste is one moment it's a solid, next moment it's a fluid, then again it's a solid and something like that. When it flows out of your tube, it's a fluid. When it rests on your toothbrush, it's a solid. When it goes on your teeth, it's again a fluid, depending on how much you shear. Making sense? Okay. It's confused by your puzzle look.
I was thinking of I was also thinking of can metal be an example of this?
Metal what?
Can metal be an example of this?
Yeah, sure. In a casting furnace, when you can pour the metal behaves like a fluid. But once it is solidified, it kind of becomes rigid. But there are also a lot of these shape memory alloys and novel materials which can actually spontaneously deform. They are very flexible. They can even be stretched, but they are still solid. So it's pretty complicated. So this is as much we'll say about what is a fluid, what is a solid. From this, what I want you to take away is there is no such thing as a fluid or a solid in the strictest sense. Both fluid and solid are ideal adjectives or descriptors. And whether a given material will behave like a fluid or a solid or something in between depends on three things, which are pressure, temperature, shear. How much you squeeze it, how much you shave it, how much you heat it. Make sense? So this connection, okay, this connection from, I'm going to write it here, the map that connects atomic or molecular scale to the macroscopic properties that engineers care, especially mechanical engineers care. Engineers are interested in is, to put it mildly, brutal. So we won't pursue that. But what we will do is try to understand try to understand under what conditions. Okay, I should write it somewhere else. Can I erase this side? Under what conditions we don't have to consider the motion of individual molecules, but rather work with ensemble. Ensemble is a synonym for the word population, which ensemble averaged quantities such as density, fluid velocity, temperature, pressure, shear stress. Pressure is nothing but normal stress. There are many more, but at least in this course, this is pretty enough for us. So under what conditions we don't have to consider the motion of individual molecules, but rather work with ensemble average quantities such as density, velocity, temperature, pressure, stress, and so on. What is this ensemble average? Can we talk about temperature? You told temperature is just the measure of the average kinetic energy of the molecules, right? What is convenient about temperature? It's a number. So temperature is written something like Boltzmann constant times temperature is the average of half mv squared of a lot of molecules where this n is practically infinite. Like you have a gas at any reasonable condition, like atmospheric conditions, the gas has a lot of atoms, and this n is typically of the order of 10 power 23 atoms or molecules, because 1 mole of a substance always contains these many atoms, right? So the temperature is essentially an average of the kinetic energy of individual atoms. It's such a pain in the neck to be able to remember the velocities of these many atoms. It's a lot of numbers. So we came up with a way. We'll define an average, call it a temperature, an average kinetic energy, we'll call it a temperature. So you just have to remember one number to denote the entire fluid or gas. That's what temperature is, and that's what I mean by ensemble average. It's just an average over all the populations. So it's like asking in this class, what is the average height of this class? I just take the height of each individual and average it. When we think of density, what do you know about density? Mass per unit volume. That is, you have a bucket of, say, fluid like water. You take a centimeter cube of that. If you weigh that centimeter cube, okay, if you weigh that centimeter cube, mass of 1 centimeter cube of that liquid is what we call density, right? It's basically density is mass per unit volume, correct? Now, what gives this 1 centimeter cube actual mass? If you zoom into this little centimeter cube, what do you expect to see? Bunch of molecules. You are at your scale, that is with your naked eye. You are seeing a centimeter cube of liquid. It looks nice and continuous, correct? Suppose I loan you the world's most powerful telescope. microscope, and you just keep zooming into that little centimeter cube, keep going higher in magnification. At some point, what do you expect to see? You will start seeing individual molecules. And not only will you start seeing individual molecules, you will notice that there is some empty space between them. Are you imagining this? Yes. If you keep zooming into that little centimeter cube of water, at some point you are going to see there is some empty space. Okay? When we say volume, we are talking about volume of that space. And when we talk about mass, can you write this mass is the number of atoms that are present in that little centimeter cube multiplied by the mass of each atom. Can you write it that way? Space has no mass. Let's agree on that. And we'll say this n or this mass is the number of atoms multiplied by the mass of each atom divided by the volume. With me so far? Are you okay? All right. With me so far? All right. What's the problem with this? So you have a centimeter cube. That's your sample. You took that and you weighed it. You got some mass, and that mass has a bunch of atoms. Now, what happens if you keep this centimeter? If you keep making this sample volume smaller and smaller and smaller and smaller, from 1 centimeter cube, let's say you go 10x smaller, 0.1 centimeter cube, 0.01 centimeter cube. You keep making this 10x smaller and smaller and smaller. At some point, what do you think will happen? You won't have enough atoms in your little volume, right? Could you see that? At some point, that little volume will not have enough atoms that this density estimate will start to fluctuate. If you go really tiny, let's say you go down to 1 femtometer cube, which is kind of 10 power minus 15 meters cube. You'll hardly find a couple of atoms in that little volume. And if you measure your density there, you will get an answer that is not the same answer that you will get at this scale. Or in other words, if you measure density with sample volumes, you start at, let's say, 1 centimeter cube. You make it 10x smaller, 0.1. You make it 100x smaller, 0.01. You are going to measure some density here. I'll call it rho naught. This rho naught will stay the same, but at some point, it'll start becoming unreliable. As your sample volume becomes too small, sample volume is too small. Are you following this thread of thought that you take a small sample? How many of you have some interest in biomedical engineering or medical science? Just asking to give an example. Okay, you know what's a biopsy, right? For others, biopsy is they take a piece of tissue. It is essentially a sampling process. And if somebody has to get that piece of tissue checked for an infection or cancer or whatever disease, especially for cancers, you have to sample where you are likely to find the cancer. Suppose the cancer is localized to the lung, but you sample in some region which is not exactly the lung, you will get a sample, but that says there is no cancerous tissue, which means you will get a misdiagnosis. This is kind of something like that. You take any centimeter cube, you will find enough atoms. You take 1/10 of a centimeter cube, you will still find enough atoms. But if you keep going smaller and smaller, at some point you will not find a consistent number of atoms that will give you the same density. Okay, so the condition is, can anybody say what the condition is? That under what conditions we don't have to consider the motion of individual molecules? From this discussion, what can you say is the answer to this question? Actually, I should have put a question mark.
You have a large aggregates of the big enough sample size, maybe molecules or particles or whatever it is.
When your length scales of interest are much larger than the scales at which molecular motion actually is important, you are pretty much okay. You don't have to give any damn about the individual motion. That is, let me erase this and then put that in words. So the answer to this question is, whenever the length scales of the flow is much bigger than the length scales, of molecular motion, we can work with ensemble averages. No need to worry about molecular motion. If we denote the length scale, that is the length scale of the flow, if we denote that as L, and the length scale of molecular motion, we'll denote that as lambda, where lambda is sometimes called the mean free path. What is mean free path? Suppose we are about 18 of us here. We all start walking around randomly in this room. Okay, we'll keep bumping into each other. If I define the distance, how far can I travel before I bump into someone else? That distance, mean free path. It is the average distance traveled by a molecule before it encounters another molecule and suffers a collision. Okay, here is a qualitative argument. I'm going to tell you this lambda scales as inversely with the pressure. Take our example. Let's say all 18 of us start walking around randomly. This room, whatever its size is, let's say it's 1,000 cubic feet, 10 by 10 by 10, just for simplicity. In this volume, 18 of us are randomly walking around and we'll bump into each other at some frequency. If in the same room, let's say there are only 3 of us, just 3 people randomly walking around, would they collide with each other more often or less often? Everybody says it is less. If only 3 people versus 3 versus 80. In which case will the collisions be more frequent? In the case of 80. That's like saying in the same volume, if I put more atoms, they will collide more frequently. Yes? And what does more density means? It also means more pressure. That is, if I apply a higher pressure, automatically there will be a higher density and they will collide more often. So I won't go into the math, but I'll just say the mean free path scales inversely as pressure. Higher pressure means lower mean free path, lower mean and vice versa. And just for a feel, this lambda is about 66 nanometers at 1 atmosphere pressure for air. This is a calculation which can be done in principle, but the details are not relevant to us. Yes.
What if we should say that the sum of the mean free paths equals L?
No, it need not. L and lambda are completely independent of each other. The fact that you flow a gas or a liquid through a pipe has nothing to do with the molecular mean free path. You have complete control over this L. You can make your pipe 1 foot or 1 nanometer. That's not related to what the fluid is.
Okay, okay. So lambda isn't the description of the flow of the fluid.
Right, lambda is a property of the fluid, correct? Is a property of the gas or the fluid. And it can be calculated based on pressure. It also depends on number density or gas density. And that's why I'm not giving you a formula because it's not something you really need to know at this level, maybe later. But what you should know is the value of lambda is actually a very small number, 66 nanometers at 1 atmospheric pressure. Okay, so think of you are designing a pipe whose diameter is like a foot or even a centimeter. Okay, so if you are interested in a pipe flow or a tube flow where the diameter is, we'll keep it simple, 1 centimeter. So if we compute or if we just compare, just when I'm about to say something interesting or important, I run out of space. Compare lambda with L. So we have 66 nanometers, which I'll simplify as 100 nanometers because I hate math. Okay, so lambda divided by L is 100 times 10 power minus 9 meters divided by 10 power minus 2 meters, which makes this 10 power minus 5. With me? The comparison between the molecular scale of motion and the macroscopic scale that our engineer cares about is about 100,000 times smaller. The molecular motion is 100,000 times smaller than what you care about. So don't care about that. Okay, and this parameter has a name. It's called the Knudsen number. Knudsen number. As long as Knudsen number as long as Knudsen number is very small, we can work with quantities or ensemble average quantities. Averaged quantities such as density, velocity, temperature, pressure, shear stress, and so on. Okay, it started here with that sample. As you make the sample smaller, this when I say 1 centimeter cube, I am implicitly saying L equals 1 centimeter. But when I am just going down to let's say I have 1 nanometer cube or 1 nanometer cube, then I'm saying L is 1 nanometer. Okay, if I calculate 100 nanometers divided by 1 nanometer, I'm getting 100. So now molecular motion is important actually, but that's not the subject of this course. We will stay away from that. We are going to stay within the regime where Knudsen number is very small, which is true for most high density, large scale flows that we encounter in mechanical engineering. Except of course you come to do research with me where we'll be mostly working with this other regime. Questions? Is it making sense or is it too dense? Yes? Are you able to follow? Okay. So here's one question for you. We talk about fluid velocity, right? You have a fan, you run the fan, the blade spins, and the gas moves along. You say the fluid has some velocity. At this moment, there is not much of airflow in this room. Of course, the HVAC is working, but we don't really feel any draft. Does anybody feel a draft? Let's assume we don't feel it. Okay, so the air is stagnant. Okay, when the air is stagnant, are the molecules stagnant? They are always in perpetual motion. That's what makes them, molecules. So if the air is stagnant and the molecules are in motion, what does it even mean to say the velocity is zero? The population is not going anywhere, but each member of that population is constantly moving around. So what does that mean?
It's relative. It's like when net force is zero, it means that the force is on one side, balance out the force, so that's zero. So the velocity is zero. Okay.
So let's say there are lots of molecules, but as a whole, they are not drifting or moving anywhere. It could mean that they are all at rest, which clearly is not the case. Or for every molecule that goes this way, statistically, there is a molecule that goes the other way, making the average go to zero. Okay, so the picture that you need to absorb . So the picture that you need to observe is molecules are in constant random motion, random or thermal motion. And this gives rise to the property of what is the number or quantity we use to denote this constant random motion? Temperature. This gives rise to temperature, which is as we defined before, is the average kinetic energy of the ensemble. Okay. When we talk about velocity, what we are really talking about is the velocity of a fluid. Let's say you have a fan, you are spinning the fan, the air is flowing, and you just pick any one point. Okay, just pick any one point, and let's say we put a measurement instrument there, and that instrument is reading the velocity for us. We'll learn about measurement instruments, but for now we are just having an instrument that gives us velocity. And that velocity is, let's say it is about 1 meter per second. Just for discussion's sake. When I say 1 meter per second, what that really means is velocity equals 1 meter per second. Every atom or molecule, So think about it this way. We are all kind of randomly moving, assuming we are like the atoms. But if the room itself is drifting slowly in a particular direction, we all both have our own individual random velocities and have a collective frame of reference velocity. That is what this 1 meter per second is. This is the ensemble average of all the molecules so that their random components will cancel out, and what remains is the systematic velocity. So whenever you say the fluid at a given point has such and such velocity, it means all the molecules at that point are drifting in a particular direction at that velocity. That's what velocity means. Okay, it's the difference between there is always motion, but there is not always collective motion. Okay. We talked about density, we addressed temperature, we addressed velocity. What about pressure? What molecular action manifests itself as pressure? Distance between? Not quite. So if you just Actually, it's much easier if you go back to your high school and they teach you there are two atoms and there is a force between them. The distance influences one quantity, which is the magnitude of the force between. So whenever we say there are some quantities that makes intuitive sense, and then there are some made up quantities. Like for example, you can understand force. It's like literally saying how hard can you punch or be punched. You can understand distance. You can understand speed. Maybe you can even understand acceleration. If you are at the traffic light and the green comes on and you just zoom into, in 40 in 6 seconds. Don't try that. Or at least don't try it and tell me I put that thought in. What is pressure? I'm struggling to understand this or connect with this quantity. How do you give a description or understand pressure? It's
How often,
I'll come to you.
how often molecules collide?
It's how often molecules collide, but the word for that would be collision frequency. Why is it called pressure? Yes.
It's the force divided over an area.
It's the force divided over area. Somebody told you that, right? If they didn't tell you that, what would you say about pressure? How would you feel pressure?
Like if you press down on something.
You press down on something, or if you know scuba diving, or you can do deep lake diving, the deeper you go, you can feel the pressure squeezing you as the deeper you go. Somebody else had something to say. Okay, you can't say that. Okay. Anybody else? Any other ways or to explain what is pressure is?
If you can like imagine like a basketball court,
Okay.
one person bouncing the basketball creates like a sound of force. You can hear one basketball, but if you have like 1,000 or 1,000,000, they all start to sound like one giant basketball, and that's the pressure. That's all those atoms colliding, like we said, over that area creates pressure.
So it kind of you kind of say the same thing in slightly different language, but ultimately it does come to how much force or momentum I'm able to transfer. But that also scales with the area available. If I have a larger area, I would transfer more force. So I have to normalize it by area, and that's why people came up with the notion that if you have a surface and fluid molecules are banging into it from every direction, it would experience a force. Yes, we get it. A molecule bangs onto a surface. There is going to be some momentum transfer. You can imagine that, right? Like this basketball example. You bounce the ball, that floor is going to feel something. Can we agree on that? And if at the same time, 10 of you are bouncing basketballs off that floor, the floor is going to experience more force, or you are spread over the entire court. And let's say in each square meter of the court, there are 2 people bouncing those balls. So the total force is going to scale with how many square meters there are and how many people there are, or how many molecules there are. Is this thread making sense? Yes? No? You're giving the same expression for both yes and yes. Okay. So this pressure is in fact force per area, but the reason why we scale it with area is if there are molecules and if they are spread out over a larger area, there will be more force as the size of the area increases. That's why we have to scale this down. Okay. So pressure would be force over area in the limit that the area goes to 0, as we have always heard. And we'll see a more mathematical definition or derivation of this in the second unit. Okay, so I don't want to be into it too much. So when you're talking about pressure, you are actually referring to at a molecular scale how much momentum are these molecules transferring with each impact with the surface. That's what pressure means. Okay, it's a measure of how much force transferred, or measure of the force transferred by molecules to material surfaces. That actually is an important statement because unless a material surface is involved, you can't know what the pressure is. You cannot know you are being squeezed unless you take a dive in the pool or lake. You can't stand outside and say my pressure would be such and such. That would be a calculation. Whereas if you have to sense it, you have to have a material surface which forms the basis for measurement. And whether you know the working principle or not, how many of you have used pressure transducers in your daily life or homes or engineering practice? Give me some examples. Where all have you measured pressure at home, at work? Yes.
That's higher.
Higher, nice. Let's list this. It's going to be fun. Okay, so you check if you go to discount tire, they'll give you that little thing. You press your tube and the pressure will pop up. There will be lines. You can read out the pressure. Good. What else?
Barometer.
Where? Context. You're talking about your doctor's visit and he took your blood pressure.
No, a barometer used to measure air pressure.
Okay, that is, I understand that is done in a laboratory. I want you to connect this course with your everyday life. So can you give me some more everyday examples?
Like for rain.
Oh, for rain, yeah, that's what I want. For atmospheric pressure measurement or like weather.
Yeah, it's the barometer used to measure atmospheric pressure.
Sure.
Predict chance of rain.
No, what you measure is pressure, but they have models that tell you depending on pressure, temperature, humidity, they tell you whether it will rain. That's a yeah, definitely. Yeah. What else? Blood pressure. I'll put that example. What else?
Airbags on the truck.
Do you really read the pressure or it just deploys when the acceleration exceeds a certain time?
Well, it's dependent on what you're towing. So if you're towing something heavier, you have to put more pressure in the airbag so your back end doesn't sag. And
Okay, so do you pump it yourself?
there's automatics and there's ones that you can't pump yourself.
And in that, is there a dial or indicator?
Yes.
Okay, yeah. So air barrels. What else? Where else have you measured pressure? Yes.
They supply general aviation.
Sure, oil pressure, pneumatic pressure, even in your car, there are gauges to read the oil pressure. Sure. Yes.
Doing load tests with hydraulic.
Yeah, that will be. I mean, it can be hydraulics, it can be automobile, avionics, they're all similar things. Yeah. Yeah.
You can measure the refrigerant pressure in the cooling lines in the HVAC system.
You can. Have you done that?
Yeah, work.
Oh, you work there. Good. So you work in HVAC and you have done, you basically read the pressure in your lines, especially when you're diagnosing if there is a broken pump or if there is any clogging in the lines and stuff like that. By the way, what happens when there is clogging in the line? Does the pressure go up or go down?
And they go.
It goes up. We'll explain this in unit 7. Why would pressure go up when there is clogging? Any thoughts?
Well, there's a clog in the line. The flow would be stopped or.
Constricted. Which is the same reason why plaque buildup leads to heart attacks and stuff. We are going to see why and why mathematically it just becomes so dangerous when the constriction grows quickly. Yeah. All right. One more example. I'll let you go.
Using pressure washer.
I'm asking for when do you measure pressure in your home? Residential units may not have this, but most commercial buildings will have a pressure gauge at the water inlet, so that they check whether the city is sending the water at the specified pressure or if there's a drop in pressure. If you go to facilities management, just walk in there and tell them you are a student, you just want to know how pressure is measured. Look at the pressure gauges for water. They may even have one for gas utility, the gas pressure. Always important to connect what you study with life. Otherwise, you lose motivation to study. This is what I've understood so far. Okay, shear. What is shear? Tangential force over an area, right? Where do we Okay, we'll start with examples. In life, when do we use shearing on some liquid to get work done? Sorry,
Brushing your teeth,
brushing your teeth. We already covered that. That's good. What else? Yes.
spreading peanut butter.
Spreading peanut butter, my favorite thing. What else? Cleaning. Can you elaborate, please?
Wiping the counter with some kind of.
So when you put the counter and you spray some solvent or you spray some soap, you are essentially using shear force to create lather. That shear force is supplying energy to the surfactants which create foam, and the foam is supposed to pull the dirt with. Of course, it also involves a concept called surface tension, but shearing is the mechanism by which you create foam. Okay, you are supplying energy by shearing. Very nice. Where else do we do shearing? Yes.
Moving furniture,
Can you elaborate, please?
like moving a chair side to side.
That is on in a floor, like solid on solid. Can we focus on fluid centric examples? Where else do you shear liquids on? Yeah, painting, any kind of spreading is shearing. You can't spread without applying a tangential force. Can be solvent, can be cleaner, can be paint, thinner, but what else?
So, writing, like using a pencil.
The solid on solid. Can we focus on fluids?
That's-
In there you have a pencil lead which is solid, paper which is solid.
Okay,
Yeah, good pivot. So yeah, pen will definitely fall under.
say,
Good, especially the old school ink pens. Yeah. Yes,
Oh, I was saying that's what I have. I use a pen.
yeah. So that is a classic example of using shearing to spread the liquid and get something. Okay. So shearing, we often, just like we wrote pressure is force times area, we don't have a special definition, but shear stress is the tangential force over an area. And again, just like pressure, we normalize it by area because the magnitude of the force transmitted does increase with area. One question though, in the case of pressure, this is, I shouldn't say force, I should have said normal force. Okay. In this case, this is tangential force. At a molecular level, nothing has changed. It's still the same molecules, they have same random motion. If a molecule, let's say I have this surface, consider I'm dropping a ball exactly vertical. And we'll just consider that as an analogy for a molecule which is undergoing a normal collision, meaning it's just vertically falling down. There is no other component in the transverse direction. So the ball will hit and the ball will bounce back exactly vertically. There is no tangential involvement. That is what manifests as pressure, the normal force. But when the same ball, instead of being dropped vertically, it is, let's say, hit at that floor at an angle. So you can resolve this motion. If it's coming down at an angle, you can resolve that motion into a vertical component and a tangential component or a horizontal component. The vertical component contributed to your pressure, the compressive normal stress. The tangential motion of the molecules contribute to shear, which is shear stress. So there is no more magic left at the molecular scale. It's just atomic, it's just their motion, but that manifests as temperature, velocity, pressure, and shear stress. It's the same thing, only we give it different names to denote different aspects of molecular motion. Is that making sense? There is no more tricks in there. It's just a bunch of molecules undergoing motion. That's it. All the consequences that we see in everyday life, they are all different facets of molecular motion. Okay. All right. So now I want to take a small detour to talk about units, because without units, I can't make anything quantitative. So we have to stop the physics oriented discussion and talk about units for a second. Um, what is a unit? Like intuitively, how do you describe unit without using technical terms? Yes. No. Okay. What I mean is, when you are coming to describe or measure something, how do you convey information? Think from that angle. You need a reference. Let's say I want to measure the length of this table. I can't use my own hand as a yardstick and say this is 3 of these. It makes no sense to you because you don't know how long this is, right? So obviously the logical step is we all should agree on some way of expressing length or measuring length, and we came up with a standard which we call unit. Except people in different parts of the world came up with their own units for length or temperature or mass. And that's why we have different systems. We have the SI system, which is accepted everywhere except in America. And then there is the English system, which is used in US. When I was a student 15, 16 years ago, I was like, why should I learn a new system of units? I'm very comfortable with SI. But the fact is, if you are used to a certain way of talking and thinking, there's a lot of inertia to change. And I can understand now why US won't change change to the metric system. You have to reorganize entire life around it. You are used to saying things in pound and gallon, stuff like that. You can't suddenly say liters and kilograms and everything. So we still will deal with both. Mostly we'll deal with SI system in this course, but we'll also do English units time to time just to keep it practically relevant, because odds are you will take up a job in Tennessee, not in England or France or maybe you. So we have units and then we have dimensions. So before we talk about units, which are more subjective, the more fundamental quantity is dimensions. So if you think of quantities, not all of most of them can be expressed in terms of something else. Like for example, you know what is Newton's second law, right? How do you define force? Force is mass times acceleration. So if I were to tell you that, how do you define, let's say, 1 Newton force? It would be the case when an object of 1 kilogram weight experiences an acceleration of 1 meter per second square. So whatever you call as Newton is not fundamental because it can be expressed in terms of kilograms and meter and second squared. Or if you don't like SI, you can do the same with 1 pound force and 1 pound force, 1 pound mass, and feet per second squared. This is subjective, meaning it's your choice of unit system, but the relation is fundamental. This is an example of a dimensional relation where you can write the unit for force or the dimension for force is the dimension for mass multiplied for the dimension of acceleration. Now, what is this dimension? If you take mass, we'll write the dimension of mass as m, meaning mass is fundamental. You can't express mass in terms of something else. It is a basic property that can't be expressed or broken down further. When you think of acceleration, what is acceleration? It's the change in velocity over time, and velocity itself is change in position over time. So ultimately, it is some length divided by time squared. Or I can write this m L, T to the -2. So the first skill you are going to pick up in this course, or maybe you have done this also in some other course, is to express any quantity in terms of mass, length, and time. So mass, length, and time, and also temperature. So we will denote temperature with theta, are fundamental dimensions that will be used to express other higher order or derived quantities. What is a derived quantity? I mean, something like force equals mass times acceleration is a definition for force. The definition. So if you know the dimensions of the right side, you can write the dimensions of the quantity being defined. Okay. Let's do some examples. Okay, it's not a very heavy concept, so examples are best. Can we write the dimensions of density? What is density? It is mass per unit volume. Oh. No, density has dimension. We'll see shortly. So dimensions of what is the dimension of mass? It's a fundamental dimension, so we'll write it as m. What is volume? It is some length raised to the third power. So this is m over L cube. So this is mL to the minus. Okay. Let's think of pressure. Pressure. So pressure is, what do we know? Force per area. Right. I use the square bracket to denote the dimension of density, shorthand, square bracket, rho. What is the dimension of force? We just did, right? We'll copy this value. That would be mL to the minus mLT to the minus 2 divided by L square. Are you able to do this? Like follow this? So this will be m L to the minus 1 T to the minus 2. You're good with that? Okay. Can we do the dimensions of shear stress? It's the same, it's stress. You call it shear stress, normal stress, that's based on the specifics, but at the end of the day, it's a stress. So if pressure is mL minus 1 T minus 2, shear stress is also the same. You all taken thermodynamics, right? Okay, so let's do this. Can you write the dimensions of specific heat? What are the dimensions of specific heat? Actually, before we do that, what are the dimensions of energy or heat? So energy is unit is joule. And how do we define energy? What are various ways of defining energy?
1/2 mv squared plus mgh.
So you're saying energy can be written as kinetic energy. That's one way of writing it. You can also write that as work done, force times displacement. You can write energy as electrostatic energy if you are into electrostatics. So there are lots of forms of energy. And we don't have to do everything, but let's say we pick the easiest example. What are the dimensions of energy? That would be the dimensions of half multiplied by the dimensions of m multiplied by the dimensions of velocity squared. Yes. This half is what we call a pure number. It has no units. It's just an exact number, half. It's not 0.499, it's not 0.501, it's 1 divided by 2, the fraction, and the origins come from mathematics. So we don't have a unit for it in this case. So it doesn't have any dimension. This is mass. This is velocity. What's the dimension of velocity? Do it in your head and tell me. Yes?
Sorry.
That is the unit, but dimension would be length divided by time. Okay? So length divided by time squared. So the dimensions of energy is m L squared t to the minus 2.
So you don't put the 1/2 in at all.
The 1/2 has no dimensions, it's a number, so you don't have to write it. If it had unit, yes, but it doesn't. We'll see some examples where it has units. If you did the work done definition, energy is defined through work as force times displacement, it would still be the same answer. Because if you write energy is dimension of force divided by the dimension of distance, that is m L t to the minus 2 times L, which is still the same. So all of these various definitions of the same quantity will give you the same dimension in the end. You can check this in every way you can. Yes.
So how is the electrical one for two, ML squared T?
So the electrical sort of has these other quantities which we don't typically encounter in this course. So I just wanted to make a point that you can define energy in many ways. You can do half kx squared, which is more common to us. Spring constant times displacement squared. Okay, we can go into this, but let's not spend time. So what I want you to do is look at okay, so they have a table for this. That's okay. Okay, so now let's do one more heat transfer relevant quantity. Can you get me the dimensions for specific heat? Can you recall what is specific heat from your thermodynamics? If you supply Q or if you supply certain joules of energy to a mass, the temperature rise is a function of the specific heat. Or in other words, specific heat is the heat added divided by the mass multiplied by the change in temperature observed. Right? Q equals mCp delta T. The first equation I think I remembered from my undergrad. So this is an energy. Okay, so this has dimensions of energy. This is dimension of mass. This is delta T, which is a temperature difference. What's the dimension of a temperature difference? Should be same as temperature, right? It's just a Kelvin minus a Kelvin or a Celsius minus a Celsius. So this is whatever is the dimension of energy, which is this m L squared T power minus 2 divided by m multiplied by theta. This T is time. This theta represents temperature or Kelvin or degree Celsius. So this will be L squared T power minus 2 theta power minus 1. You can do many more examples, like every quantity that you can think of or you newly encounter, you can make it a practice to write out the dimensions of that quantity if you know how it is measured or calculated or defined. What is heat transfer coefficient? Anybody taking heat transfer now? Even if you did, it's just week one, so maybe they wouldn't have talked about it. So heat transfer coefficient is Q equals H A delta T. The amount of heat supplied to a surface produces a temperature difference. The proportionality constant is called the heat transfer coefficient. So H may be measured as Q divided by A times delta T. So this is energy or heat supplied. This is surface area. So this would be ml squared T power minus 2 divided by L squared times theta, which makes this m T power minus 2 theta power minus 1. Okay. The reason we do these dimensions are, if you want to go from one unit system to another, okay, you can easily take, so if you just remember two things. One is, let's say we talk about SI and we talk about English engineering units. What is the unit for mass? 1 kilogram, 1 pound mass, right? Length, 1 meter, 1 foot. Time, 1 second, still 1 second. Temperature, 1 Kelvin, 1 degree Rankine, or sometimes 1 degree Fahrenheit. So it makes unit conversion much simpler if you know fundamentally what are the dimensions of a given point. Okay. So I needed to introduce that before I could talk about fluid properties. So, but doing good on time. So far what I've talked about from the beginning to now is section 1.1 to 1.3. Okay, now I'm starting section 1.4, fluid properties. Okay. So the first of those properties are density. What is density? You know that it's mass per unit volume, but that's not the point of this discussion. Do we have an intuitive feel as engineers for the density of the fluids that we do handle or that we expect to handle? Like if I ask you the density of water, it's some number, it's 1000 kilograms per meter cube. But if I ask you the question, let's say you take SAE 40 grade motor oil and you pour it on water, are you going to expect it to float or sink? So you're saying it's denser than water? Anybody expects it to float? You can expect, it's okay to have. I honestly don't know what you'll have. I have to look at the numbers. Yes.
I'll see it float.
Float.
Yeah.
Okay. So if you look at table 1.5, if you have your book in front of you, I said SAE 40, they have SAE 30. SAE 30 has a density of 912, and you know water has a density of 999. So it is going to sink, but just about, because the densities are almost same. But you get the point that it's a liquid whose density is comparable to water. Okay. Do you know what is the densest liquid that there is, that we know under atmospheric pressure conditions? Mercury. Any guesses on the density value relative to water, like X times bigger than water? Yeah. 5.
Yes.
Yes. Okay. It's actually 13.6 times bigger. That's why we use it in barometers, because to measure a pressure difference using mercury, the height difference will be manageable in millimeters or centimeters. If you build the same barometer with water, guess how tall that column needs to be? Exactly 13.6 times taller, because to produce the same pressure difference, the height has to be 13.6 times bigger. Right? It's like saying delta P is rho G delta H. If for water, this is 1000, and for mercury, this is 13,600. If you swap mercury with water, you have to get a deflection that is 13.6 times bigger. So your column, if it is 1 meter, it has to be 13.6 meters. Okay. So density is an important property. What I am asking you to do as homework is look at tables 1.5 and 1.6. Not like you have to memorize it, but be familiar with the density of commonly encountered fluids. Okay. Anybody has any idea what the density of blood might be? Is it like similar to water or less than?
Like pretty comparable.
Similar, because blood is almost like 80% water with a lot of other cells and components. So the properties are pretty much dominated by water. Same thing for soap solution. Soap is like almost 99% water, and then some surfactant which does work. In the same sense that this building is like 99% empty, except where the structures stand. Okay, here's something I do. So when I go to Starbucks, I always ask for no foam on my latte. Because why? A foam is mostly air. And I'm no aerosol scientist who's going to pay for air. I want milk, and that's what I'm paying for. I'm not paying for air. Anyway. All right. So that's density. That's covered in section 1.4. Okay. So go through section 1. Actually, I'm basically asking you to follow up with the lecture by reading these sections. Whatever I did previously was section 1.1 to 1.3, 1.4. So when it comes to gases, we have this famous ideal gas law or ideal gas model, and it goes as pressure is rho times RT. You've seen this in your thermodynamics when we talked about or when you discussed equation of state. Can somebody tell me what are the conditions in which the ideal gas model is a good description of a gas? It's a reasonable, accurate description of a gas. Okay, before we answer that, what does this equation actually tell you? You see the equation P equals rho RT. What does it mean?
Pressure is equal to the density times, I forget what constant that is.
Okay, let's call it gas constant.
Yes.
Okay.
And then temperature.
So that would be the literal interpretation. But what I'm trying to get at is, if you are having a canister of gas, you can put a piston or you can apply some force to squeeze the gas, and you can set the pressure. That's what you do in your bicycle pump, right? You push the piston, you pressurize the gas. Temperature, you don't control it in your bicycle pump, but in principle, you can put a heating tape or a cooling circuit or a PID controller, and you can hold temperature at a certain value. Or in other words, if you take a gas in an enclosure, you can set pressure and you can set temperature. You take a gas, if you squeeze it to a certain degree of pressure and you set a certain temperature, you can't also decide how much gas has to be in there. That's what this equation says. It's a constraint of three variables that in an experiment you can only control two of them. If you control pressure and temperature, you don't have a choice on density. That's what this equation states, that there is a very specific relation between density as a function of pressure and temperature, or pressure as a function of density and temperature. I won't go further because that's actually what equation of state means, and that's thermodynamics. We don't want to do that. But this model, when is it reasonable? For that, you have to know what goes behind this model. when people start thinking about gas, this is probably misinformed, but this is the first theory that came up. They thought these gas atoms just float around. They don't have any force between each other. It's like we are all walking randomly in this room, but we are all blind, or we have shut our eyes and we don't see each other. Occasionally we will bump into each other and only then we'll know there are others in the room. Ideal gas model mathematically codifies that idea that atoms just travel in straight lines and they just travel like that until they meet another atom and collide. After the collision, they revert back to being blind. So it is a model that ignores intermolecular attraction or forces and assumes that they are all like billiard balls. That's why sometimes it's called the billiard ball model. You play snooker, you hit the balls, they travel in straight lines, until they collide, they don't know that they are approaching each other. That's how they picture molecules in this equation. This is an extremely good approximation. Here's the answer I'm giving it. It's an extremely good approximation at low pressures and high temperature. Sorry? Somebody said something? It is an extremely good approximation at low pressure and high temperature. You agree? Question?
Yeah, relative to what, I guess?
Brilliant. That's what I was going for. Somebody has to ask me, hey, what is low, what is high? Is it 1000 Kelvin? Is it 10,000 Kelvin? Somebody has to tell me that. Relative to the temperature or relative to the conditions at which the gas may condense or liquefy or even solidify. Sorry, I've been writing this somewhat deep here. So let's say it in words. You can also watch it later in the video. It's a good model for a gas at low pressures and high temperatures relative to the conditions at which the gas may condense or liquefy. Let's take a very simple example. Can we use this to describe nitrogen gas at room temperature and pressure, meaning 1 atmosphere pressure and 25 degrees Celsius?
Yes.
We can. And if we can use it to describe nitrogen at room temperature and pressure. Anybody knows what is the liquefaction point or temperature for nitrogen? It's about minus 212 degrees Celsius. I mean, I may be off, but it's somewhere in that minus 200 Celsius ballpark. So relative to that minus 200, room temperature is how many degrees hotter? Around 200. So it is high relative to its condensation point. So this is a good model for nitrogen at room temperature. And if the temperature is even hotter, it only gets a little bit better. Let me ask you another question. Is this a good model for water vapor? Don? Yeah.
Yeah, it depends where you are.
Let's say I am at 102 degrees Celsius and 1 atmosphere pressure. No, because I'm kind of on the line of condensation. If I drop a couple of degrees, it will start condensing. But if I have superheated steam, which is at, let's say, 400 degrees Celsius and 1 atmosphere pressure, this is actually a pretty good approximation to describe the state of that superheated steam. It makes sense? The brilliant insight is it's a good model for low pressure and high temperature relative to where it will condense. Okay, so throughout our discussion here in this course, if we encounter gases, we are going to deal with only atmospheric pressure or nearby atmospheric pressure and nearby room temperature. We are not going to deal with low temperatures or cryogenics or such kind of exotic situations. So for us, this is a very good model for gases that we will use. That makes sense? For us, if you have to describe or calculate the density of methane at 2 atmospheres and 300 Kelvin, you can use the ideal gas model. It's pretty reasonable way to do this. Okay, so this is covered in section 1.5. So the main problem or type of application of this ideal gas model most often in this course is to use it as a way to calculate density. Your specified pressure and temperature of the gas, you will be required or the density will be needed. So you plug in the values and get the density. The smart or the very careful engineer will add one more statement saying the pressure, temperature is such and such, and the condensation point of this material, which is methane or nitrogen or helium or carbon dioxide or whatever, is they will look up the condensation point of that and add a statement saying relative to that temperature, this is high enough, so I am using this density equals P divided by R. When you go for a job, like when you are in the corporate world or when you are in a power plant or when you are actually part of a team, a multi-step team that does engineering, it all comes to documentation. Your ability to compute something is almost taken for granted because most of you will have that ability. It's not a special skill. But what will make you stand out is if you are a good, diligent communicator and you document the steps and the justifications for calculations. So suppose you're not used to this practice of stating the assumptions. What will happen is someday you will take this equation, apply it for very low pressure and very low temperature, where that gas is probably already liquefied, and calculate an erroneous density and use that as the basis for the next step in your design, and something might blow up somewhere. And when that something blows up somewhere, do you know what they do? What companies do, what governments do?
Investigate.
They investigate, they look for documentation, they look for the signature, who signed off on this design calculation, who signed off on this estimation. And when your name shows up as the person who approved the wrongly calculated density, guess who's getting fired? So in this course, it's just a matter of a couple of points. But in real life, it could be liability, it could be accountable. Okay, so don't take this lightly. If you are going to use this calculation in my class, you will state that it is appropriate to use it, and only then you will use it. Make sense? You in your exam, I'm going to look for that sentence. Since the temperature is high enough relative to the condensation point, I am using this. I need that statement. I am not testing you on your ability to do arithmetic. I know you can do it. Is it clear? All right, we'll continue next on Tuesday. Yes.
Will we be expected to keep a sheet of condensation information? That's.
You mean the data value?
Yeah.
Yeah, if a gas is there, I'll provide.
Very specific.